It's an easy 12-liner. F1, this doesn't exist, okay? This is one of my deepest wishes, that F1 would be a field, but it isn't. Except for the third exercise. This gives me terminal cancer. A huge thanks to my Patreon supporters for making this episode possible. Mathematicians, welcome back to our video. First things first, alright? So, if you're new here to the show, the hard exam playlist will be down there at the top of the description. Also the playlist where I work through a few of those hard exam problems, alright? So where I solve them. And also, if you have any hard exams with a high failure rate that you want to send me that I should present on the show, then the link will be down there at the top of the description, the email address. Alright, now for the main part. Hard exam series yet again. We're going to talk about linear algebra and analytic geometry today. And here's the basic overview of what the video is going to be like yet again. At first, some data about how many people participated, which semester, etc. Then we are going to dive into the main thing, the linear algebra exam. And after that I'm going to tell you about a few reasons why so many people have failed in the first place. And I'm going to start this video off by reading what a student has put up here on the copy of the exam, alright? I translated it into English. The person wrote, "Over 90% of students failed this first semester exam. As far as I am concerned, none of the exercises being presented here have been covered in any way similar to any homework assignment. Exercise 1 has been covered in Professor Bra's lecture or lecture notes partially." So now you have kind of an idea what's going on, alright? So the professor presented some stuff that maybe it wasn't really part of any kind of exercise, so no one was really prepared for that. And here's some data. First semester exam. So I can't really tell you how many people participated. I can only speak out of my own experience that about 200 to 250 people go into mathematics each and every year. So those are first semesters. They either become some kind of teacher, they are just there to be there just for fun in linear algebra, or they are going to become a pure mathematician or an applied mathematician, so Bachelor of Science in some way. So those are the kinds of people that are going to participate in this exam at the end of the first semester. And to be honest, this thing is kinda easy except for the third exercise. This gives me terminal cancer. This exercise is extremely hard and it took me ages to get through this thing. So yeah, maybe it's just because I didn't know about some theorems whatsoever. It's just my opinion. Also, do not forget to check out my second channel. We just started a new series there. Link will be at the top of the description. And also don't forget to check out my new website. I made it with Notion and I linked papaflammy.engineer there. Link will be also down there in the description. We are going to dive into this exam now. As always, I have translated the German version for you into English using LaTeX. So this is the original version. 4 exercises, 12 points each exercise, 48 points in total. You need to get 50% of all the points to pass this exam. And here's the English version that I have translated for you. We are going to dive now into this exam and we are going to see what it actually looks like, alright? If you are wondering, by the way, this exam has been created by the same person who created the algebra and arithmetic exam where 96% failed. He's a substitute professor sometimes for linear algebra. In the normal case, he only does algebra and arithmetic. So now you know where he does come from. So he comes from field, group and ring theory. And this is mostly the most hardcore thing at university for most undergrads. We're now going to dive in and we are going to see what's the big deal about this exam here. So like I mentioned before, we have 4 exercises, each with 12 points. You need 50% to pass this thing. And the first exercise basically just deals with a 3x3 matrix in some random arbitrary field. We are going to call it F. and we want to discuss the diagonalizability. I have practiced this word so often in the last few days, such that I can say it nicely in this video. Just listen to it. Diagonalizability. Diagonalizability. Alright, so we need to check for the diagonalizability, great pronunciation, Papa, of A. And we want to explain thoroughly, and yeah, we want to explain thoroughly why it is diagonalizable, and also we want to take a look at the characteristic of F, if there's something we need to take into account in order for it to be diagonalizable. So here's the basic structure, what you need to do. So at first this was our matrix A, and we need to calculate the characteristic polynomial in some way of A, which is nothing but, well, the determinant of A minus, well, then we have our eigenvalues that we don't know yet. We are going to get 3 eigenvalues, we don't know if they are distinct yet, times the identity matrix in 3 dimensions, and we need to set this equal to 0. After you get this whole polynomial, it should be something like lambda plus 3 times lambda minus 2 times lambda minus 1. Good thing is, a lot of stuff cancels out. You can just make use of Sarrus rule here, I'm terribly sorry, and the eigenvalues are what you have here on the main diagonal basically. So those are the eigenvalues, and now we need to take a look at the characteristic, because it can happen that if you are in a field with characteristic 2 or 3, so a field F can only be a field if the characteristic of it is prime, P is prime, alright? So this is what we need, 2 and 3 are prime, so we don't need to take a look at F1, this doesn't exist, okay, this is one of my deepest wishes, that F1 would be a field, but it isn't, alright? So yeah, so we need to take a look at the cases where we have modulo 3 or where we have modulo 2, corresponding to those eigenvalues. If we are in F2, then for example A is going to look like this. A in F2 is going to be, alright, so 2, so all multiples of 2 are going to be 0. This gives us 0. And then negative 1 is exactly 1 in modulo 2 yet again. So 0, 1, 0. Then we have 0, 1, 0. And then 1, 1. And negative 3 is exactly 1 yet again. This is what it looks like in modulo 2. And yeah, this thing is actually not diagonalizable if you check for everything. This just has to do with the eigenvalues that we are going to get out of it, and it just doesn't happen. It's just not diagonalizable, because 3 in modulo 2 would be 1 yet again, and it just doesn't work out. So the geometric multiplicity isn't equal to the algebraic multiplicity in this case. So for F2 it doesn't work. For F3 it should work out. In my opinion, it should work out. Correct me if I'm wrong on this one. So this is all you really need to do for this. Otherwise, in each and every other field, it's just going to be diagonalizable. You just check for the dimensions of the eigenspace and the corresponding eigenvalues with algebraic multiplicity of 1 then. If A is indeed diagonalizable, then calculate a T element of GL3 in this field F with T to negative 1 times A times T is a diagonal matrix. Alright, so yeah, calculating this T is just a straightforward process. You just need to find one that does it, and then you are just going to go through this whole thing. You are going to take A minus the first eigenvalue, for example, times the identity matrix in 3 dimensions, times some vector x, y, z is equal to the 0 vector. So we want to find out the kernel, so the homogeneous solution for each and every eigenvector. This is just a property of eigenvectors. You're going to do this 3 times overall, and after that you are basically done with this. You can find yourself a T where, so this is the vector v1, and then our T is nothing but v1, v2 and v3. Okay? That's going to be our matrix. Then you can invert it, check for invertibility, and then you are basically done. That was the first exercise. Really easy. First exercise is really easy. Same spiel for the second exercise. Show that K forms a field under the regular matrix multiplication and addition. You just go through the field axioms. Means distributive laws, then we need a commutative group with respect to plus, and we need a group with respect to times. Alright, so yeah, and this group with respect to the multiplication is just going to be without the 0 matrix in there. So it does work out. You just go through all those axioms. It's going to be really easy. Next up is a bit more work. We need to show that a V being defined like this is a vector space over K. Over this field K that we have here. It's really easy to show, just go through the vector space axioms. It's really easy. Then note that plus in V means matrix addition and K times V is just a scalar multiplication. We know this, so matrix product. And what dimension does V have over the field K? You can use some dimension theorem or something, but there's actually an easier way. We can just go through all the elements in here in K. What elements do we have in K, for example? In K we have, let A be equal to 0 and B be equal to 0, then we have 0, 0, 0, 0, 0 plus 0 is 0. If A is 1 and B is 0, then we are going to get 1, 0, 0, 1 plus 0 is just 1. Then A and B are both equal to 1. We are going to get 1, 1, 1, and 1 plus 1 is 2, and modulo 2 is nothing but 0. And the last element that we are going to get is when A is equal to 0 and B is equal to 1. So this gives us 0, 1, 1, 0. Those should, oh no, 1. I'm terribly sorry. Those should be all the elements. 4 elements, you can do some combinatorics here. Also, V has 4 distinct entries and they are out of set 2, so 2 possibilities for each slot makes 2 to the 4th power. 2 to the 4th power. Yes, I'm terribly sorry, it's going to be 2 to the 4th power. This means this is 16. So meaning the dimension of V over K is going to be 16 over 4 is going to be overall 4. So this should work out. I hope this is correct. This was just my understanding. So you just can go through the elements here, element wise. And this has been the second exercise. Really easy to, just a lot of work. Also for this exam you have 3 hours of time, just as a little side note. Now here comes the worst exercise in existence. Seriously, this thing sucks so hard. It took me ages because I didn't know about a few theorems when it came to diagonalizability and minimal polynomials. So let A and B be element of Q and N, where A squared is N times AB squared is N squared times the identity matrix N dimensions, and AB is commutative, AB is BA, and this is equal to N times A. We now need to show that F of A minus B is equal to the 0 matrix. You just go through the calculations. You have F of X given, so that means if you plug it into F of X, you are going to get F of A minus B is going to be A minus B times A minus B minus N times A minus B plus N. I'm terribly sorry. So this is just what it looks like, and those are just calculations. It's an easy 12-liner, alright? So this is just really easy calculations. Nothing to really do here, just use the properties that we have up here. That's the easy part. You can get 1 or 2 points out of 12 from that, but now here comes the worst part. And we now need to check whether A minus B is diagonalizable or not. If you have the theorems at hand, it's not going to be a problem. But if you don't have the theorems at hand, it's going to be extremely problematic. So the first one is, we have that F of some matrix M, so A minus B is just a matrix M. If we have F of a matrix M being equal to the 0 matrix, then this implies that the minimal polynomial in this matrix M is going to be dividing some F, for example. So this F being this one right here. So we don't know if this thing is actually the minimal polynomial, but yeah, it could be smaller, but that's really not the point here. If we have this, then a matrix, that's another theorem, a matrix is diagonalizable over some field F, if and only if, so that's an equivalence, the minimal polynomial splits into linear factors over this field. So this is basically what this theorem says. So our F of M is equal to the 0 matrix. This implies that the minimal polynomial divides F, but this also implies that our minimal polynomial splits into linear factors, and this is equivalent to the statement that the matrix is diagonalizable over this field. It's some kind of theorem. I didn't know about this. Cedric Brendel helped me with this, so thank you, Cedric, very much. I didn't know about this theorem. And yeah, I would have been seriously fucked in this exercise when I would have had it in the first semester. So I really wouldn't know about this theorem, probably. Even though I went to the lectures, I wouldn't know about this. And probably this and the last exercise are the whole reason why so many people failed this thing. Next, is the matrix, blah blah blah, I called it B, index ra, bra, diagonalizable. And this thing is absolutely ingenious, this last part. It's really ingenious. If you take a look at this matrix, we know that our B is nothing but, well, what do we have? This is just a whole bunch of ones, so this is just a matrix in n dimensions with ones everywhere, minus, well, a matrix with n's on the not main diagonal, okay? Minus n times a matrix where we have zeros everywhere except for the not main diagonal. This is really similar to the exercise we had on the algebra and arithmetic one. Now, if we just check for some properties here, let us bring it back to F. Let's call this thing B1 and this thing right here is B2. Okay, then we have that B1 squared is going to be, if we square this, we are going to put this on front, then we have in the first spot 1 plus 1 plus 1 n times. This is just going to be n, and we are going to have n everywhere. Meaning overall this is n times B1. N times B1, this kind of rings a bell. We had a squared is equal to n times a. Now we have b squared is equal to n times b. Oh, that's absolutely ingenious. And now for b squared, we have that b squared is nothing, but if we put it on here, 1, 1 and everywhere zeros on the other places, meaning this is just the identity matrix. If we put an n to the front, it's going to be n times the identity matrix overall. Yes, if you include the n in B2, then it's just going to be n squared times the identity matrix. Let's put it like this. This is just the same as b squared being equal to n squared times the identity matrix. Meaning overall, those matrices that we have defined here basically go by the rules of a and b up here. Then we do subtract b1 from b2. This is just a minus b basically. And f of a minus b is going to be equal to the zero matrix. And we know that it's going to be diagonalizable by this piece of shit that we have here. And then we are done. And now for the last exercise, I'm not going to go into too much detail about this. This is just a standard surjectivity and injectivity exercise that you are going to find in each and every linear algebra lecture note out there. And you are going to have a ton of solutions out there on MathStack Exchange. Only one or two words about this. This result in linear algebra is extremely important because it basically just says overall that if it's bijective, for example, that we can express each and every linear transformation as a matrix if it's finite dimensional. This is just a really big important result here, and it also says something about those linear transformations. For example, if you want it to be bijective, then it needs to be a square matrix, for example. So this one is really important. Now we went through this exam, and now a few last words. So we went over this exam, and now once again we would like to talk about the reasons why so many people failed. And I believe it's kind of clear why so many people failed. So we had those first few lines where a student said from her experience that none of this really has been covered by Professor in any way. And yeah, this is kind of the worst thing. So if you get only really rigorous and never practice all this stuff that you need to apply here in those exams, then you are pretty much freaked. So there's no way around it. This is probably by far the greatest factor why this happened. Also in a normal case in linear algebra, in the first semester, students won't get any real rigorous proofs that they need to do. So as for the linear algebra courses I visited, there wasn't really any rigorous proof that you need to do. And I know from my experience that a lot of people struggle with surjectivity and injectivity, and yeah, many people suffer from not being able to pull off proofs in the first semester. Me included, I couldn't do proofs in the first semester. It took me ages to get some proofs done, alright? So yeah, other than that, third exercise is just an absolute killer. This thing is so annoying, and if you don't know about the theorems that I have presented here, then you're also pretty darned. And that's the thing that also happened to the last exam I have presented to you guys, so the algebra and arithmetic exam. We had that the first two exercises were doable, but the last two exercises weren't really doable for most students. And those get you half of the points, and getting a perfect score on those two is already kind of hard for most students. So if you do one little mistake here and you can't really get any points here, then you just fail, obviously. So yeah, few reasons here at hand. Not enough preparation, not enough good exercise preparing you for this exam. First year students aren't really good in general, in normal case, so you just started out with university, so you don't really know what's going to come. And yeah, just is what it is. But he's not doing linear algebra in a normal case. So as far as I'm concerned, he only did linear algebra as a docent two times already. So it was last year, and this thing was from 2002 or something, I can't remember. So this is just the bright side of things, so he doesn't do linear algebra normally. I hope you did enjoy this video. If you did, please like, subscribe and recommend channel if you like. Also, by those t-shirts I created, life is complex, really fits the linear algebra feeling here. And other than that, I thank you guys for watching. Don't forget to check out my shop, check out the website, check out the second channel. This is really important to me. And up until next video, I'm wishing you guys a flammable day. Don't forget to send me your hard exams. Ciao!
Ich habe sein Arschloch gefilmt. Und Anton ist so garstig gerade, der will ihn gar nicht reinkommen lassen.